Okay, we're going to talk about mortality probabilities, mortality rates, and hazards. And we start off with this figure, this diagram that you've seen several times before. It's a figure of the L of X curve. You know that the area A plus the area B approximates the NLX. And we also know from before that NQX, which is the probability of dying in the N years following age X, that's going to be NDX, the numbers of deaths. That's the difference in height between L of X and L of X plus N, divided by L of X. So it's the proportion of people who die in the N years after age X. And then we've already been introduced to the mortality rate. That's NMX. That's going to be NDX, the numbers of deaths, divided by that area A plus B, or NLX. So obviously, if you take a look at the formulas, at the equations, you'll see that the mortality probability is not equal to the mortality rate, that they're different. They have the same denominator, they have the same numerator, but they have different denominators. A plus B, which is NLX, we have a formal definition of it, which is N times LX plus N plus NAX times NDX. But we know that if NAX equals N over 2, which is for most of our age groups, except for the very, very, very young and the very, very, very old, then if that's the case, then we can simplify things a little bit, and we can say that N LX plus N over 2 times NDX equals the N of NLX, which simplifies to NLX plus N over 2. What is NDX? It is the difference between L of X and L of X plus N. So we end up with this formula that we often see in books, which is N times L of X plus L of X plus N over 2. That is the N times the average of L of X and L of X plus N. So just to put things in context, NLX is roughly N times L of X. You can see that if this curve L of X is shallow, then roughly, just in terms of an approximation, this bigger rectangle is going to be N times the height L of X. So what we actually know is that this area is somewhere between N times L of X and N times L of X plus N. So we're going to say that L of X, which is the area under the curve, is going to be somewhere between this bigger rectangle, which has height L of X and width N, and this smaller rectangle, which has height L of X plus N and width N. So that's what we're saying here, that this thing is bounded. N of L, N times L of X plus N is less than NLX, which is less than N times L of X. Now we notice that NMX is just our rate, which is the deaths, NDX, divided by the person years. It's NLX. So if the denominators are ordered in the way in the box, then when we put them as a reciprocal, we flip the inequality sign, or we can write the equation backwards, and we can see that it must be the case that if we take NDX and divide them by each of these, then we have NDX over N times L of X which is less than n dx divided by n lx, which is less than n dx divided by n times lx plus n. Why does that matter? This thing in the middle, of course, is nmx. And this thing over here, if we look at that, that's nqx. So this thing is nqx divided by n. So we have that this thing is less than, but it's not far away from. So just as a rough rule of thumb, nlx roughly being, n times L of x, it means that nmx is roughly equal to, so nmx is roughly equal to n dx divided by this thing, nlx, which is equal to nqx over n. So if we have a 5-year probability of dying, like 5q10, then the mortality rate, which is 5 years wide, is going to be roughly, because it's a 1-year rate, it's a 5-year rate, but we always express it in terms of person years. So it's going to be roughly n times smaller. So either we can say n times nmx times the rate gives us the 5-year or n-year probability of dying, or we can say that the mortality rate, we take the probability of dying and we divide it by the number of years, n, and these are roughly, that's going to be approximately, so you can know the order of the magnitude of these things. So let's rewrite this. Let's rewrite this one more time. And we know that, let me think a second. How do I want to write this? No, maybe I'm going to skip. I'm going to skip a little bit. Okay, so I'm going to say that nmx equals n dx divided by n lx. And I'll ask a question. What happens as n goes to 0? So we want to know what is the limit as n goes to 0 of n times mx of the mortality rate. What is that? Well, let's see, the limit as n goes to 0. So what we're doing is, let's take a look at we know this is our x, this is our x plus n. We're looking at this area, and we want this mortality, n dx. So this is lx, this is lx plus n. As n gets smaller and smaller, what we're doing is we're making narrower and narrower strips. And we're going to look at the mortality rate as we get closer and closer. Now, what was n dx? Let's see, so the limit as nmx goes to 0. That equals n dx divided by n lx. And what we said was that should equal n dx is L of x minus L of x plus n. That's the numerator. And then the denominator we had, for most age groups, this is pretty linear, so it's n times the average of L of x and L of x plus n. And I'm going to rewrite exactly this thing just one more time. I'm going to write it in a slightly different way. So the limit of this thing equals the limit as n goes to 0 of this thing. And that equals the limit as n goes to 0. I'm going to rewrite this as in two pieces. I'm going to take this n, I'm going to say L x minus L x plus n over n times 1 over L of x plus L of x plus n over 2. And what is this thing? What is this piece? If you look at that, it is the limit as n goes to 0 of the difference between two pieces divided by n. That's the slope. That's actually the negative slope. And what is this thing? This thing was supposed to be the average of these two. So this piece is going to go to 1 over L of x. So this thing, let's remind ourselves what the definition of a derivative is. It is L of x plus n minus L of x divided by n. This is the other way around. It's L of x minus L of x plus n. So that's minus the derivative. So this thing is going to be minus the derivative, d dx, of the L of x curve, and this times 1 over L of x. So this piece goes to this, and this piece goes to that. So I'm going to rewrite that one more time. It's minus d dx L of x divided by L of x, and you'll recognize that we've seen that before. We saw that earlier. This is a proportional change in the derivative. That's going to be equal to minus the derivative of the log of L of x. And we call this thing the hazard rate at age x, and we give it a special symbol, and that is mu. That is the Greek letter mu of x. And that is so important, I think I'm going to write it one more time. So the hazard rate is an instantaneous mortality rate. So whenever you hear the words hazard rate, you just think that's a mortality rate. And we give it the symbol mu of x, and it is equal to either the derivative of L of x divided by L of x, or else it is also the derivative of the log of L of x. We have two different ways to express it. They're equivalent. Let's see. So if we have mu of x, it is a mortality rate. So mu of x, I'm going to say minus d dx divided by L of x. that means that mu of x, the hazard rate, times the population age x. This is the number, the mortality rate, the hazard rate. That's going to be the change in the L of x. So that's going to be the slope. So that turns out the change in the number of people looks like the mortality rate. As I said, the hazard rate looks like a mortality rate times the people. So this thing is just a first order ordinary differential, first degree ordinary differential equation. Just like we saw earlier when we took a look at the differential equation way to look at the growth rate. That's one way to think about it. The other way is via the log. Also, if mu of x equals minus the derivative of the log of L of x, then we can take the integral of both sides, and we can have the integral from 0 to x of mu of y dy. I think I need a minus sign here because it's a minus, we're multiplying it, and that's going to equal the log of L of x divided by our radix, L0. So if that equals the log, then it must be the case that L of, if the log of L of x divided by L0 equals minus this thing, then it must mean that L of x over L0 equals e to the minus integral from 0 to x of mu of y dy. And that must mean that L of x equals L0, our radix, times e to the minus integral from 0 to x of mu of y dy. We can split this latter piece up. I'm going to rewrite that one more time. We can split that up into different pieces. We can split that up into 0 to 1 of mu of y dy plus minus the 1 to 2 h2 of mu of y dy plus minus the integral from h2 to h3 of mu of y dy all the way up to age x. So that's going to be from x minus 1 up to x of mu of y dy. That's all of, that's a minus sign, that's all in the, as an exponent of e. Each of these pieces, remember now, when you add up things, they look like you're multiplying e to each of these separate pieces. That's how we can get the summation of all of these pieces in the exponents. So it's going to turn out that, in general, each of these things is going to describe the probability of what? How did we get from L0 to Lx? We saw that earlier. We saw that the probabilities of survival multiply. So that was L0 times 1p0 times 1p1, 1p2, all the way up to 1px minus 1. So that must mean that each of these pieces equals the probability of surviving. And this way of looking at it, in general, we can note, since the probability of survival multiply, we know that npx in general is going to equal e to the minus x to x plus n of mu of y dy. And so these things are called cumulative hazards. We can accumulate the hazards, integrate over all of them, and that will give us the probability of surviving from age x to x plus n. And this is important because we tend to model in terms of the hazards, in terms of these instantaneous mortality rates, rather more than we model on the probabilities of dying. So when we talk about Gompertz mortality or the other mortality models, we'll either be talking about the NMXs or the mu-Xs. And I think that'll be enough for the now.